Welcome back, class, to Electromagnetics. Today we want to continue our review and expand on that a little bit. We're going to talk about sinusoidally time-varying fields today, which is the primary field that we will deal with in electromagnetics. First, let's take a look at our historical background for today. Again, looking at the lives of some of the people who helped form the field of electromagnetics and influence it. Give you some clues for this person today, see if you can guess who it is. First, he was educated at the University of Göttingen and also Emmanuel College in Cambridge. This individual started out work as a physician and worked at and taught at the Royal Institute. So here's an image of this person. Give you one last chance to see if you can guess the identity. And this person is Thomas Young, lived in the late 1700s, early 1800s. So what are some of the things that are notable about Mr. Young? First, you may recognize his name because he did some work in mechanics of materials and developed Young's modulus for mechanics of materials. So if you've had that course, you've probably seen that and are familiar with that. In his spare time, he was a major contributor to deciphering Egyptian hieroglyphics. Up until this time, it was a mystery of how to read that and interpret it, and he did a lot of work in that field. He also established the wave theory of light with his interference or double slit experiment. And I want to talk a little bit about that here in just a minute, because that's a very important experiment, both in electromagnetics and if you read further on it in relativity and quantum mechanics and stuff like that. Finally, though, I think the coolest thing is he was known as the man who knew everything. So history tells that there was not a subject that you could come up with that he didn't know at least something about. And if you read historical accounts, whenever they would have balls or parties or gatherings that everybody found out that he was going to attend, they would go to the library and try to find, some obscure pieces of knowledge to try to test him on this. And according to the legend, he never failed. He always knew a little bit of something about everything that they could come up with. So kind of an interesting fellow. So I want to expand a little bit on the double slit experiment. Maybe you've done this in a physics class before. If not, if you ever have the opportunity, I would highly recommend it. But the basis of this is what Young did. He was kind of in the lab, or I guess experimenting, and he had a light source. Probably wasn't a light bulb at that time. It was probably a candle or something else, or a lantern. Anyway, he took a barrier there and put a small slit in it and let the light shine through it. And when it did on the wall, of course, what one might expect, it was bright in the middle and tapered off or got dimmer as it went to the edges. So being the inquisitive mind that he was, he said, well, I wonder what would happen if I did two slits, thinking that there would be two bright spots with it fading off in both, in all directions of those. Well, that's not at all what he saw. So what happened was, when he did the double slit experiment, he had a pattern much like you see here, or dark and bright, dark and bright, dark and bright spaces. Well, this upset a lot of people as they didn't understand what was going on. Here's an actual photograph of a single slit on the top. You can see, as we expect, it's bright in the middle and kind of fades off as you go in each direction. Then the double slit is pretty striking. I mean, you see all these patterns of bright spots and then dark spots in between. And so Young took it upon himself to explain this, and what he did is he kind of drew on the analogy of when you throw two rocks or two stones into the water and it creates these waves. And so his conclusion was that light must also travel in a wave pattern. And so what happens is, as these two sources of light come through, you'll have instances where they are in phase with each other, and then instances where they're out of phase with each other. And of course, when they're in phase with each other, they add together to form the bright spots, and when they're out of phase with each other, they cancel each other out and cause the dark spots. And so we can even model this today with some modeling softwares that we have. So this is one that I found that I think shows a pretty good picture. So it's like you drop the two stones in here, and as it moves forward, you can see that the patterns interact, and that's why it's called interference. Interfere with each other and cause the speckled pattern on the wall here. So interesting experiment. The reason why this is important to relativity and quantum mechanics is that this causes some, this experiment can cause some issues when you start to deal with it mathematically, of the causality, in that the light going through this slot, or the photon, must have some, it appears, must have some predetermined knowledge of what's happening to the photon over here. And so it's pretty interesting. If you get a chance to watch a YouTube video on it, or read on it, I would recommend it. It's pretty interesting stuff. There's still some questions about that we don't fully understand. So back to our lectures. Again, we're still in part 1. Today we're going to look at section 1.4, sinusoidally time-varying fields. And again, this will be the primary model for electromagnetics moving forward. So, sinusoidal representation. So, since the scalar components of electromagnetic waves are most commonly sinusoidal, we want to now take a look at how to represent these components mathematically. And so the general equation for a sinusoidal component is this guy here. So hopefully this isn't your first time to see this, but this is a sinusoidal function in its general form. So let's take a minute here and kind of break this down, make sure we understand everything that's going on here. So the first thing we see is the A, and so this will be the amplitude, or the max and min of the wave. So as the cosine function varies up and down, the maximum that it's going to be, because the cosine varies between 0 and 1. So when it's 1, your maximum will be A, and of course when it's 0, your minimum will be 0. So that's the amplitude of the wave. The omega we see here, that's times the t, we call this the radian frequency, and so this is in radians per second. And so this gives us some knowledge of how periodic this sine wave is. We notice that it's defined as 2 pi times f, so we probably are more familiar with the f term as the linear frequency in hertz, so how many times it's cycling per second. And so that's the f term and how it relates to that. Of course, the final term is the phase shift, and so what this does is, when this is a non-zero value, it'll take the sine wave pattern and slide it either left or right, whether phi is negative or positive, along the x-axis. So the maximums and minimums will occur at different points on the x-axis. They'll still be the same distance apart, but they'll be slid up and down the axis. So one thing to keep in mind as we move forward is this argument of the cosine function. This is referred to many times as the total phase of the wave. So the omega t plus phi. So this tells us pretty much everything we need to know as far as the location of the wave and what's happening to it at a certain point in time. Of course, we still need the amplitude if we need to know that max and min, the absolute value of that. But from this, we can tell when it's going to occur, which is many times is all we need to know. So taking all that, we have a representation here graphically of a cosine, of the sinusoidal cosine function. So you can see we have our max and min, so the A and minus A and 0 are the 3 points that you're going to find from that. This cosine does go from -1 to +1. You can see that the omega t, that tells us how close together these peaks are. So as the omega increases, these will start to be squashed closer together. And then this phi term is what determines where we are on here. So you can see in this case, phi must be some non-zero number, because otherwise, if phi was 0, this maximum should occur at 0 and should be right here. But because phi is not 0, it's actually slid the graph down the t-axis just a bit, so that gives us our phase shift. So in real world, we don't see perfect sine waves. You know, if you were to think about that, I would maybe take wherever you are, transmit a sine wave, and someone in Chicago or New York received it. It's not going to look exactly the same as what we sent. And so the reason for this is because the sine wave is dampered. And so this is what the equation looks like, how we take that into account. So everything's the same here except for this e to the minus alpha z term. And so this is what we call our dampening term. And so what this does is this e to the negative alpha z creates this envelope, is what we call it. It's decay, envelope of decay curve right here, both in the negative and positive axes. And so what this does is this governs what the maximum and minimum value is. So this number will always be less than 1 and be decreasing. So if this number is decreasing times a, of course, that would naturally cause our amplitude to continue to go down. Now we have ways of dealing with this for different types of technology, but it is more representative of how sine waves actually travel in real life. So let's take a minute and look at the vector components. For sinusoidally time-varying vector fields, each component is represented by a sinusoidal expression. So remember, we have those components on the AX, AY, and AZ unit vector coordinates. And so being that this will be a vector field, we will have representation for each of those. So for each component at any point, the tip of the vector is oscillating back and forth in a line parallel to the plane or direction of orientation, and each component then is said to be linearly polarized. And I'll show you a picture of this in just a second, but all the components are always linearly polarized. Now when we start to put components together, we start to get other types of polarization besides linear, and we'll look at some examples of that here in just a minute. So if we apply a sinusoidal vector or function in the x direction, it should look something like this, and this is like the graph we saw earlier, right? So we will see that as we move forward in time, that our function, of course, oscillates back and forth. And so one way to think about it for the linear polarization is if you were to look in this direction back into the t-axis. So we're actually looking from the side over here, and so that's what this depiction is right here. So what we would see is the vector going up and down, up and down, up and down, and this dot here is the t-axis, right? And so this is why we call this linearly polarized, because it's just going back and forth in a line, right? And so it's actually going back and forth in the x direction, so we'll say that this is linearly polarized in the x direction. Now if we were to do the same thing for the y direction, what we have here then is if x is going up and t is going this way, y would be the third axis here going in and out of the board, so that's why you see this y here. And so this is actually like it's been laid down flat, and so you can see it's going up and down in terms of y. It's not doing any motion in terms of x, right? So these are orthogonal. And so again, if we look back down the t-axis here, this dot being the t-axis, we start to see it's still linear, but now it's linearly polarized in the y direction, right? So this is linearly polarized in the x direction. It just makes a line going up and down, and this is linearly polarized in the y direction. So that's just going up and down. So let's talk about electromagnetic waves then, what kind of polarization they can have. Those are just the components. So if we take two sinusoidal components that have arbitrary amplitude but are in phase with each other, remember we talked about the total phase, that is the phase arguments are equal. Example of this would be if we had F1 and F2. So we see these can be two components, one's in the x direction and one's only in the y direction. Now F1 and F2 don't necessarily have to be equal. We said they could be arbitrary, but what has to be equal in this case is these arguments of the cosine function have to be identical. So if we have this condition, then the resultant vector f, which would be f1 plus f2, is now a linearly polarized function with an angle of alpha. So the alpha can be calculated by taking the inverse tangent of fy and fx, or in this case it's f2 over f1, and that should be a constant, and so that will show us how much it'll tilt. So it may not necessarily be all in the x, or it won't necessarily be all in the y. It'll be some angle offset between x and y. That's what this alpha term is telling us. So here's a graphical representation of what's going on with linear polarization. So again, here's my F1. So remember, it's going to be going up and down, up and down. So that's what you're seeing here. Shrinking down, goes to nothing, goes back down, down further, comes back up. So we still have that sinusoid there if I'm just following just the X components, right? The laser's following that. So in the Y direction then, we'll have this same type of thing, but it's harder to see because it's a two-dimensional representation. But this one's at the maximum here, shrinking down, goes to nothing, reverses direction, maximum reverse, sinks down, back and forth. So as these two components do that, you can see the resultant here then is just going back and forth at this angle, and so that's what that angle alpha is. So it's still linearly polarized. It's just not linearly polarized in the x or the y. It's linearly polarized at some arbitrary angle. And so when we have this condition for an electromagnetic wave, this is what we call linearly polarized. So here's a animated GIF that kind of demonstrates what's going on here. So as you can see, the red and the blue, those are your F1 and F2, and so they're going back and forth. So the resultant would be adding those two together. So my red pointer here would be where the resultant would be as I add those together roughly. And so you can see I'm just going back and forth in a line. So like I said, this is linearly polarized. So another type of polarization we can have is circular polarization. So if we have two sinusoidal components that this time have equal amplitudes, remember before we could have arbitrary amplitudes. That's what gave us the alpha offset angle. But if we have equal amplitudes and they're orthogonal and they differ in phase by 90 degrees, an example of this would be if we had F1, so this is kind of what we had before, right? There's F0 times the cosine function. But then our second one, this is going to be different. So our amplitude here we see is the same, but now instead of the cosine function, we're doing the sine function. Of course, the sine function is by definition out of phase of the cosine function by 90 degrees. So this gives us our 90 degrees difference here. And so again, this is just the x component, and this is just the y component. So this will be varying on the x-axis, and this will be varying on the y-axis. All right. So if we look at this one, then the resultant vector, which would be f, which is going to be equal to f1 plus f2, is said to be circularly polarized. And we can determine its magnitude here by taking the magnitude of f. So here we just take the magnitude of our original definitions of these vectors. And when we do that, you see we'll get f naught squared, and then we'll have sine squared plus cosine squared. Well, by definition, sine squared plus cosine squared, when the arguments are the same, is a trig identity equal to 1. So this goes to 1. We have f naught squared, square root, which just gives us f naught. So that would be the amplitude, or would be the radius of this polarization. So the resultant vector f, which again is equal to f1 plus f2, still has this angle alpha, but this angle alpha is now varying. Before, the alpha stayed the same, remember, going back and forth, but now alpha is continually changing. And so if we take the definition of alpha, which is the inverse tangent of fy over fx, again it's just the inverse tangent of our two vectors, we see that things all drop out here as we take this inverse tangent, and we're left with just the argument, omega t plus phi. So again, as this t changes, because we're dealing with radian frequency, it's just going to continue to go around and around on the unit circle, right? So here is another graphical, two-dimensional graphical representation of that then, right? So if they're 90 degrees out of phase, the x component is maximized and the y component is minimized here. So as we go to here, as alpha moves around, we'll see that they're both at about half at the same time. We come over here, now the x is out of phase 90 degrees is 0, while this one's maximized. And again, we continue to go around. So again, if we follow the x component, we see it's still the sine wave as you follow my cursor there. Again, you can't see the y because we're in 2 dimensions and we're looking at straight in from the wrong axis. But again, as we add these together, then you see that the overall resultant vector magnitude stays the same, or the length stays the same. And so now we get this effect that it just appears to be spinning, this resultant vector. And so again, I have an animated GIF we'll see on the next slide to show this. So here's the animated GIF that kind of gives a visual representation of circular polarization. So here again, you can see the x component is linearly polarized, going up and down, the red arrow. And then again, you can see the y component is linearly polarized, again, going left and right. That's the green arrow. But you can tell that they are now out of phase with each other by 90 degrees. And so now as we add these together, it just makes the vector appear to be spinning, the resultant vector. So this is called circularly polarized. So before it was linearly polarized, and now we're circular polarized. So one minor change that we can have to this, and my GIF here is messing up a little bit, but you should be able to get the picture. If we still had the circular condition where one was 90 degrees out of phase with the other, but the amplitudes were different, you can see here that now instead of a circle, it's going to create an ellipse. So it's elliptically polarized. We don't deal with this very much in industry. We do some, but usually we only deal with linear or circularly polarized. Those are the two primary types of polarization. So let's look at a quick example. So we're given a scenario here, and we're being asked to determine what is the polarization of the resultant vector. So this vector that we are given, F, is going to have two components, F1 and F2. And they are defined here below. So F1 has two components actually. It has one in the x direction and one in the z direction. So we'll say an amplitude of 3 in the x direction with this cosine function, and then one that's -4 in the az direction, again cosine omega t. So when we look at F2, F2 only has a component in the y direction, and we notice that it's 90 degrees out of phase with the F1 vector. The argument's the same, so there's no phase shift, but it is 90 degrees out of, no additional phase shift. It is 90 degrees out of phase just because of the difference in the trigonometric functions. So we first note here that F1 consists of two components, which I just mentioned, that are in phase opposition. So linearly polarized with a magnitude of 3 squared plus -4 squared, which is 5. So the magnitude of this guy is 5. So this means that it's equal to the magnitude of F2. So while this has two kind of squirrely looking components, the overall magnitude of this vector is going to be 5. So as we continue to look at this, we also note that if we take the dot product of these two guys, and we should be able to recall this from the last lecture how to do that, we take 3ax minus 4az dotted with 5ay. Well, remember, this is, we can distribute this throughout here from what we learned the other day. And so if we take ax dot with ay, that's going to be 0. That means they're 90 degrees out of phase. And then if we take az and dot with ay, that again is going to be 0. So the dot product of these two vectors is 0. This tells us that these vectors then are perpendicular to each other, which that's important. So we've seen now that the amplitudes are the same. We've seen that they are perpendicular with each other. That is, they differ in phase by pi over 2. And so, and that's confirmed because one's governed by the cosine function, the other's by the sine function. And they both have the same phase argument. So now we're starting to learn a little bit about these components to our resultant vector. So hence, if F1 and F2 then are two linearly polarized perpendicular vectors having equal amplitude, but differing in phase by 90 degrees or pi over 2. This is the definition then of circularly polarized. So this vector, the resultant vector, if we were to look at it in that, like I had that animation before, and plug these vectors in, the result we would get would be a circular polarized vector. So hopefully you can see the steps here. I'll probably have some of these in homework that I want you to figure out, and this is the way we do it.